Those of you who are not in ASMT is a graduate student group. We do a lot of interdisciplinary work. It started about 12 years ago by Professor Gronsky and Professor David Atwood. They had a joint student collaboration, material science, and sort of X-ray science. And it sprang from there. A lot of students do nanomaterials, which involves either biology, material science, mechanical engineering, electrical engineering, and physics, pretty much interdisciplinary. But we've sort of branched out to do applied physics, applied chemistry, spectroscopy. There's someone in the group I know who's even working on cloud structures in Jupiter, and doing simulations there. So we're a pretty diverse group. And with that, I guess it's time. I'd like to introduce our speaker, Zhang. And he is currently the chair of the Berkeley NSF Nanoscience and Technology Center here on campus. And he did his PhD here actually a few years ago in mechanical engineering. Since then, he's taught at Penn State and UCLA, and about 3 years ago he decided to come back to Berkeley, because he loved the area, and continue as a professor here. He will now be speaking about his research in nano-scale plasmonics, metamaterials, and their applications. So help me thank the speaker.
Thank you, Andy. Good morning, everyone. And it's really a pleasure to give a talk. This is probably my second talk in AST. First one was given to engineering physics students for undergraduate, actually. So we have an undergraduate, actually graduate. And this is a wonderful event. First of all, let me welcome all the prospective students visiting here today. We have a ring, which is probably the first big one in a month or 2 months. But I heard from people come from Midwest, and this is better than snow. So let me welcome you, all of you, and people from the coast side of Boston, and also as far as from China. So this is a very interesting and exciting event. So I'm going to actually describe some of our research, our past research in my group, okay? And current research. For some of the students this afternoon, I will actually probably give you a lab tour and show you a little bit more. But those are the slides I often use for conference. So bear with me. I don't have really what our kind of ongoing project, but this is mainly our sort of past. I'm going to speak about the topics on the nanoscale plasmonics. Then I added actually metamaterials, which is intimately related with nanoplasmonics, and also, of course, the applications. The interest in my group in general we're interested in looking at the fundamental science that enabling possibility of future technology. That we emphasize the science in a way that we're looking at the possibility that explore the science never discovered before, and of course has a perspective in the applications. So this is our vision in our Nanoscale Science Engineering Center. Not my vision, actually, it's the whole center's vision. We have about 20 professors from Berkeley, Stanford, UCLA, UC San Diego, and Los Carolina. So we have actually a group of mathematicians, physicists, chemists, and of course engineers, to looking at the futuristic nanosystems. And this, again, this cartoon shows what we are pursuing, and not necessarily we are achieved yet. So we're looking at the future nanosystems is integrated system that not only electronics, but also could be mechanics, for example, nanofluidic sensors, and also biochemical sensors or biomedical sensors. And of course, you have to have electronics to do computing and making decisions. And nanophotonics, of course, is one of the major drive in this center. And here we show a few applications that we are pursuing as a group of faculty. The group, 3D terabyte memory, we are collaborating with a quantum research group across the bay in Palo Alto, in HP major research group. We're looking at the next generation of memory device and for high density nanowire-based devices. And this is the ultra-sensitive biosensors. Recently, we have also successfully launched an NIH actually sponsored nanomedicine center that focused on how we designed engineering and new physics to enable the new biotechnology. And of course, many of you familiar with nanofluidics, nanofluidics, where a group of other faculties also pursuing. And myself also involved with the nanophotonics, where the compact light source, especially we're interested in looking at the single photon light source, for example, as well as the below diffraction nanoscale interconnect for optics. So let me talk about starting here, the research in my group. Let me first actually introduce the concept of metamaterials. Meta actually in the dictionary, if you go to Web's dictionary or some other dictionary, means actually go beyond ordinary. So it's a material beyond ordinary properties. And if we look at the atomic level of the crystal structure, and some of you familiar with the solid state physics, where you have a given translational and rotational geometries. And also, in addition, each of the atoms are made by from chemical tables, where you know that about 100 up to 200 types, right? And so there are two limitations. One is, number of atoms you can engineer. Second, the geometry and translational both symmetry, translational and rotational symmetry. So one can think about, well, if I bring these later atoms to a bigger scale, let's say to a scale 100 times or 1,000 times or million times bigger. So we're talking about some of the entities we call meta-atoms, where it is not the real atom, but quote by quote here is entity. It could be a quantum dot and could be microscale beads, could be even a much larger meter scale. So this is sort of scalable. Now, what we learn actually, you can build something similar to atomic scale crystals. But however, now you could have, because it is relatively larger, can be a 10 nanometer all the way to, well, right at 100 micron, but could be much larger. Now we are also doing at a centimeter scale. So this lattice size can be really, depend on how you fabricate it, it can be a quite different scale. And also each of these quote by quote meta-atoms can be actually a physical entity that you ascribe the properties, such as you can put a little current on that, sort of have an artificial spin. And you can have actually very soft static charge, and you can have ionic crystals. So in addition, you put those meta-atoms into, for example, PDMS rubber, okay? Embedded quantum dot or something in the rubber. And you can achieve the strength. You can stretch the rubber. You can achieve the lattice size, extend 100 times, 100% of the strength. Now, if you look at later crystal silicon or gallium arsenide, if you have a 1% of strength, it's huge. So that gives you a lot of possibility to tune the properties. And as we know that in later crystals, you have this electronic band gap, where in these crystals, first of all, you can have actually easily have optical band gap or electromagnetic band gap in general. And some of you say, well, this could be a photonic crystal, familiar with. This is actually, the photonic crystal is related to this, but there's a big difference. The difference is photonic crystal, typically their lattice size or constants are at the order of the wavelengths. So that this actually is a sub-wavelength structure, such that because of lattice constant is much smaller than wavelengths, you can use the mean field theory to ascribe it. For example, you can attribute that effective properties, such as electrical or magnetic properties, we are going to discuss later on. And you can build the something like sodium chloride-like compound structure as well to achieve additional tuning. So this actually are defined typically artificial composite at sub-wavelength scale. Generally, you can view that as a homogeneous media. Of course, we are looking at unprecedented physics or properties of those materials, and that usually are not exist in the later materials. Finally, that you can actually, well, third, actually, you can have, because it's bigger, okay, it has the about a few nanometers at least, or a micron size. You can use the computer-aided design to use a top-down manufacturing process to make it, such as e-beam lithography or a microlithography. So you can embed the defects. So now, many of us knows that if, for silicon devices, if you want to dope the boron or phosphide into the silicon wafer, you can pretty much control the concentration of the dopant inside of the silicon wafer or crystal. But you cannot really, generally speaking, define a foreign atom such as boron inside of the silicon crystal in XY dimension, right, precisely. But here, because it is larger, you can use an E-beam fabrication or something to engineer those defects or dislocations. Of course, we are looking at very exciting physics and applications. So in about 7 years ago, that Sir John Pendry, he's a physicist, theoretical physicist in Imperial College in London, that proposed an array of very interesting structures. First of all, actually, I'm going to go to details of this, the magnetic activity without magnets at very high frequency. And this is very significant in the terms of the, historically, we don't have magnetism in optics. By the same token, you can structure the materials that to form artificial plasma. So you can engineer the magnetic response as well as the electric response or dielectric response. By combining the both actually mediums of negative property, you may be able to construct piece of media, so-called negative index, electromagnetic index, or optic index. That gives you the possibility, for example, one of the outcome is the imaging beyond diffraction limit. As we know that diffraction limit is the fundamental limit in optics. So I used this cartoon actually 6 or 7 years ago when we started the first US metamaterial program. We actually, again, where this is cartoon, don't, because a lot of reporters say, well, this is probably something we already realized. No, this is actually the perspective show you there's possibility to go in very small dimension for imaging. So applications are very exciting. Now, nanoscale imaging, if you can build this so-called super lens, high throughput nanolithography, by the same token, imaging and lithography are reversed process. Also, many of you probably familiar with the medical imaging use the magnetic resonance. One of the bottleneck for current magnetic imaging is that the resolution is about sub-millimeter size. So if the doctor wants to know from MRI that the tumors, how big or something, that actually is the resolution limit. If you want to do even a smaller resolution with magnetic imaging, you have to really tune up the frequency of the oscillating magnets. And that is actually has a bottleneck limit because later magnetic frequency are limited from magnetic later materials. That actually, if you can really push up magnetic response at very high frequency, you flip these dipoles at optical frequency, essentially that's a possibility to increase the magnetic imaging resolution. Of course, this enables the whole array of nanoscale integrated photonic circuit where you can do we are going to show some of the possibilities with the surface plasma propagations. And of course, the biosensing is very exciting. So the first lective index media was constructed in the UCSD group by Schur's group about a year after Pendry's theory. But this is at the microwave range. So it's rather in the low frequency. And at this frequency, we have plenty of later materials to behave as the magnetic response. But this actually, so these are the meta atoms. It's a centimeter size, about 1/2 centimeter size. So it's a big, because the wavelength of microwave is big as well. So everything scale with the wavelength. But this is, the wavelength is still much larger than the lattice size of this. So why the magnetism at optical frequency is interesting? As we know from the optics book, that index actually is equal to the product of the electrical magnetic properties, okay? In this case, epsilon mu. Now, however, at optical frequency or very high frequency, the later materials magnetic response fade away. And I'm going to explain in a second. That actually, in the optical frequency, we typically drop off the mu set equal to 1. So this is all the optics engineers works with, the n square equal to epsilon. And that actually has been for many years in the optics textbook. Now, why is that? Because in the later materials, that as we know that from the physics, college physics, that the electrical response from the materials are based on the monopoles. the electron charge moving around. Magnetism, however, so far is based on the dipoles. And people are still searching for magnetic monopoles. But, so that actually, all the later material we are found at the later are based on the dipole. And those dipole form a domain, a magnetic domain, and, so that the response is the domain response. And by nature of the dipole response, that is much slower than monopole response. That actually gives all the later materials magnetic response up to about 100 gigahertz. Okay? Above that, all the magnetic response are fade away. There are only a few actually crystals shows a very weak and narrow response above this, only a few gigahertz, few hundred gigahertz. So Pendry's theory is quite revolutionary in a sense that you can construct the artificial structures. In this case, is a ring of these cylinders, and the cylinders are two concentric cylinders. This is the top view, okay? So there's two metal sheet form cylinders. Each of these you can view as a meta atom, and it consists of billions of atoms, of course, real atoms, but itself is an entity. This can be constructed by metal, for example. Itself doesn't have magnetic response at this high frequency. But however, as you can see, actually this top view of each of the cylinder, if you excite this entity with external field, magnetic field, that magnetic field will introduce immediately the induction current around the metal loop. At the same time, these two forms a capacitance between the two layer of the cylinders, right? So you have actually inductance and capacitance, and that leads to the so-called LC circuit, or a resonance. That resonance gives you the overall magnetic field here around this entity can be larger than excitation field or lower than that. So you could have a paramagnetic or diamagnetic response. And this actually can be simply calculated with affecting property. Again, in the photonic crystals, you cannot ascribe this affecting property. While in the nanomaterials, you can do that because all of this, you make sure this actually size of this and also distance of lattice size is much smaller than wavelength. So you can, when you excite electromagnetic wave or optical wave, as long as this lattice size is much smaller than wavelengths, you can view that's a homogeneous response. So we decided actually to early time, that was about 5 years ago, we decided to test this interesting theory by fabricating these magnetic structures, artificial magnetic structures with copper, for example. Itself doesn't have magnetic response at very high frequency. And we are looking at the terahertz range where most of nature materials doesn't exist any magnetic response. And this is the basically microfabrication, and each of these atoms is about 26 micron, so it's not small. This is our analytical calculation that shows actually, this is real part of the mu magnetic permeability, that shows you indeed actually it can go beyond 1 or below 0, so could have a elective value as well. And this clearly is a resonance-based phenomena. As many resonance-based phenomena, you have a very large loss associated with that as well. So experiment was conducted with a free space FTR measurement. You have actually incident beam comes in, and we measure the ellipsometry parameters that essentially the reflection and the ratios with the S and P. And you make sure actually this magnetic, the blue actually component, it has a component perpendicular to the ring, such that generate oscillating current. And that also coupled capacitively with the two rings, gives you collectively the magnetic response of this metacrystal. So these are the 3 samples corresponding the 3 different frequency, and essentially are 3 different sizes. So by changing the size of the ring, you can essentially tune the resonance frequency. That gives you a resonance at about below 1 terahertz or a little above the terahertz. So this is tunable with the size. This is our simulation result, predict the peak of the resonance versus the experimental result, which agree pretty well. This is in collaboration with the UCSD Basov and Smith group. We actually believe this is the first artificial magnetic response at far infrared demonstrated. Since then, the race starts, and many groups across the world that start to race who can make the higher frequency. So actually, almost concurrently, we start looking at the structures. It's a little bit different design. Now, these are each metal atoms are fabricated. So you see array of them form a crystal and fabricated on the quartz. And those are nanoscale now. Each of these about micron, but actually the fine structure here, the ring, the width of this is about 100 nanometer. The gap is about 70 nanometer. So it's really a smaller structure. By structuring smaller, you push up the frequency. So this is actually designed at middle infrared. And the measurement is very similar. You have incident beam comes in, and you measure its epsimetry response, and you have actually magnetic component perpendicular, almost perpendicular to the ring, such that they generate the resonance through the inductance capacitance coupling. So here's the brief result of the first, actually, we believe the first response of the at 6 micron middle infrared. You can see actually quite pronounced response of this magnetic structure. And of course, by changing the size of the geometry, you can tune the response from actually 6 micron all the way to 10 micron in this case. In this case, also, we are very interesting the atom-atom interaction as well. That is also very interesting to look into through a near labor interaction. And also, German group at the same time report even higher magnetic matter material at about 3 micron or 100 terahertz. This is about actually a 1 year, less than a year span. So it was a really hot kind of race. And this actually measurement, however, was not directly magnetic response, rather is electric dipole-induced magnetic response. But actually, the measurement actually itself is pretty solid. Now, why this is interesting? So if we can really push the magnetic response to a high frequency, such as infrared or optical, and we can engineer this magnetic response not only positive but active. And also, we can engineer, I don't have time to talk about the electric response on the plasma part, but generally using nanowires, you can introduce the plasmonic response. That gives you possibility easily lective epsilon. By combining the mu and epsilon, both are lective, the causality requires that the index of this medium, if you use this piece of things to construct a medium, that has to be lective. That actually, so why this lective indexing is interesting? That actually, as I mentioned that before, this artificial structure which has lective index in optics could be useful for imaging below diffraction limit. So what's wrong with a positive media? We have eyeglass or lens you use in the lab. So if you do imaging, essentially, it's a Fourier expansion essentially from object to the image. And you expand that object, the electric component, with a variety of k vectors. And these k vectors, actually, the kz is along the trivial direction, and kx, ky describe the informations of this object in the lateral direction. So if the kx, ky squares are relatively small, then omega over c term. So because momentum got to be conserved, so kx, ky, kz square has to be equal to omega over c square. So if this, however, is smaller than omega over c term, and this kz can be real, so that it's a propagating wave. So that can transport this Fourier component from object to the image. However, so this imaging is essentially Fourier transfer process. However, if the kx, ky are large, for example, there are some very nanoscopic features on my face you want to image, that corresponding very large k vector. That actually force the kz become imaginary because kx, ky, kz has to be equal to omega over c. So if this is larger than omega over c, that gives you kz imaginary. That corresponding so-called evanescence wave, where it's not propagating, it is a decaying field. So essentially, for most of imaging, what you collect is a propagating wave. And that is imperfect. So you lost some large k-vector Fourier component. And that gives you so-called diffraction limit, where the diffraction limit is the largest k you can collect. It depend on the this cutoff. So what actually this lective index media give the theoretically at the time, 7 years ago, a possibility that if you plug in epsilon mu are elective and you calculate the transmission coefficient, essentially it's a field actually ratio after this media and before that. So that can be exponentially grow over this media with the thickness of the media. And that is very interesting because that gives you the hope that this growth or enhancement can compensate the decay in the real space or positive media. So in the elective media's growth could be counter this. But however, actually the physics actually is really Pendry described that your excited surface resonance that established the field actually is growing rather than decaying. And now, however, some of you may saying that, well, this is violating the energy conservation, how you can grow something out of nothing. This is actually, keep in mind, the propagating wave carries the flux. But however, evanescence wave doesn't carry the flux. It's a field oscillation. So it's basically a field redistribution. So here actually shows the two nanowires, our early calculation, that you can actually image separate about 80 nanometers. You can image them with excitation of different surface oscillations. In this case, can be a surface plasma, okay? And that not only you can have a reduction, but also enlargement of the image. So you can do a little bit of both. But this actually brings an interesting electrostatic limit where everything smaller than wavelengths, that you can work only with epsilon. You can forget about the mu. And that gives you the special case, essentially, of this elective index. So you can use a piece of metal, such as gold or silver, but itself is not elective index media. It could give you very easily epsilon become elective. And at the electrostatic limit, electrical and magnetic part are decoupled, where you can actually use only epsilon to do the same function. But however, this is considered as a special case. So this opens a very interesting new interesting science engineering paradigm for imaging and lithography. For example, this is the plasma actually concept where what is the plasma? Plasma is the electronic oscillations collectively at interface between dielectric and metal, okay, at certain conditions. So itself is not fermion, it's a Boson. It's electronic collective motion. So this is the omega k actually relation where this straight line shows linear optics typically people are working on. So when you try to increase the resolution of imaging, you try to use oil immersion or some high index media in between, right? So you tilt this line essentially by index n here. But later materials only gives you probably index the largest about 2 to 3 at most, such as diamond. But I mean, using diamond between your object and the lens will be too difficult, if not too expensive. So you can access a little bit of higher k. The higher k is the one we want to access for better resolution. So k is inverse proportionally to the surface information size. The other way is increase the photon energy, where like Intel are doing, try to push the EUV lithography, or even like Professor Atwood are doing the X-ray lithography. So you increase photon energy, you can access a higher k. And however, there is also a cost associated to build this very large instrument. Surface plasmas, as a red curve shows here, offers a different approach where actually you can excite at the visible frequency or a little bit UV and very large k vector. So actually, if you excite it around here, a very large k vector wave can be, surface wave can be excited. And that gives you so-called optical frequency and X-ray wavelengths. Now, X-ray wavelengths really means this large k vector and surface waves. So those are not the propagating waves in the free space. It's bounded at surface. And next question is, what are the interesting physics and engineering technique we can use to look at this possibility for next generation of lithography and imaging? So in the early 2000, there was a lot of debate in the PRL and even Science Nature about whether this superlens theory Pendry proposed was legitimate. So a lot of papers say, well, this is wrong. So we decide actually to do experiment. Really, well, first of all, before we do that, we do believe that theory, and we through some analytical calculations. So the first experiment designed to test this theory was actually using a piece of silver film and using the laser roughness as a coupler. And you have actually a laser beam comes in and excited surface waves. Now, because of the random nature of the surface roughness, that gives you all kinds of a K-vector. So only the K-vector matches with the surface plasma will be significantly enhanced through this media. And what we want to see is whether this enhancement, this amplitude ratio, is exponentially grow with the thickness of metal film. This is sort of counterintuitive because if the field usually are die out with the thickness of the film increases. But this is what the theory actually the key proposition of the theory. So however, even this is enhanced, and this enhanced to this side even is that is still evanescence mode or surface mode. How you're going to detect at far field? So in this case, we use a piece of hemispheric lens, okay, and that actually couples this special K into a propagating wave. That actually you can measure at the far field. And this is actually far field measurement because this is polarized light, so it's not symmetrical. So what we see actually is a cone, plasmonic cone actually coming out. And this cone gives you a lot of rich information. By actually plotting this over the angle direction. So this is angle direction, and you can have, with a different metal thickness, you can plot this angular distribution that essentially gives you the solid angle of information of the scattering. Okay. Essentially, you can treat this as a weak scattering because the surface roughness is only nanometer scale. So this is a typical weak scattering optics, where the TP is what we want to determine. And this is what we measure at here. And SK is the surface Fourier surface randomness of Fourier component, which is a coupling strength. You can essentially use AFM to map out the surface roughness and do a Fourier transfer, and that's the Fourier component. Essentially, it's a coupling strength for this given K. And this is dipole function can be calculated. This take care of the polarization orientations, okay, in theta and phi. So essentially, we can determine this because we know the wavelengths. We know this from FM measurement of the surface roughness, and we know the scattering of the plasma cone. So this is what the final result. And these dotted actually numbers are experimental value, and this blue line is the theory. Essentially, actually, what we measure with the increase of thickness, indeed, actually, we see a rapid increase of the transmission coefficient, okay, square here, okay. And this is counterintuitive, but actually, it is predicted by the theory and as plotted here. But however, this growth is not, growing infinitely because actually any metallic system has a loss. Real system has a loss, such that when the loss is pronounced, very pronounced as you increase the amplitude at one of the surface, that decouple, essentially finally decouple these two surface resonance, that damps out the significance of this enhancement. So there's an optimum sort of 60 nanometer of the range that you can observe this interesting phenomena of the Pendry's theory. Next question is, of course, so if this is possible, can we demonstrate the so-called superlens? What the superlens really mean is you can image an object that typically gives you the K-vector much larger than propagating wave. So it's evanescence wave. But however, we want to use a slab of silver lens to image it, record on the other side with photoresist in this case. And this is our simulation, that full wave simulation, that indeed actually we can observe, if everything goes right, we can observe this image on this side. PR means photoresist. Now, of course, in the imaging or in the calculations, we have to assume each of the interface perfectly flat. But this actually simple assumption made about 4 years effort. We try to struggle how we make a flat surface. So this is final result. About 3 or 4 years later, we successfully demonstrate this superlens image. Essentially, we have object here ascribed by the FIB. Basically, you cut it with focus ion beam. And those structures are a 50 nanometer open up and down. So it's not big. You may say it was very thin film. But however, now each of the layers, we have to make sure are flat less than 1 nanometer. And that actually was the struggle actually over that we have to develop various of innovative fabrication technique to try to do that. Because if this is more than, let's say, 3 or 4 nanometer, the whole image, the plasma resonance actually at the surface are scattered away. Okay, so you don't have a clear image constructed. So this is the 60 nanometer nanowire array spaced by 60 nanometers. Typically, you cannot observe in optical microscopy. And however, here you can observe pretty clearly, especially in the Fourier spectrum. But here you can see it's not perfect image still because actually these are we believe some of the metal actually has it's not single crystal. It's has certain grain size effects that scattered the surface plasma as well. And in addition, we demonstrate also arbitrary patterning imaging. So you write the nano, which the width of that is about 50 nanometers. But however, the character itself is about 1 to 2 micron. So character is diffraction limited. You should be able to see the character overall structure. But now if you do a Fourier transfer of this image or this object, it's all kinds of k-vectors. The smallest k-vector is corresponding, or largest k-vector corresponding this very small feature size, and small k-vector corresponding the bigger overall size. Okay? So without the superlens, you will see overall structure. And both actually of this imaging takes 30 times of experiment to get the best contrast. So this is the best contrast after 30 exposures. So you can see actually the width of this. So even though you should be able to see this diffraction limited, because this is about 1 to 2 micron, right? You should be able to see it. But however, the sharpness of this is about 1 wavelength size, which is a diffraction limited, okay? About 1 lambda, 350 nanometer. However, with the superlens, you will be able to see that way below diffraction limit, about 80 to 90 nanometers. So that shows you actually, indeed, actually, this is the imaging below diffraction limit. So this is nice to demonstrate the physics of the superlensing. But however, one thing we have to be sure that is now we do have a limitation. In this experiment, the image is projected just outside of the silver slab. So image is at the near field as well. But this is a projection essentially. So for any practical applications, this can be limited because you have to put your detectors or CCD next to the lens itself. So building a far-field optical nanoscope has been our group's pursuit last few years. Really how we bring the image from the near field to the far field. As we know that the optical microscope has been very instrumental for many areas of science and technology development. For example, modern biology is actually benefit greatly with this invention of optical microscope. But however, it itself has a limitation. It has a diffraction limit, typically about half of the wavelengths. Half micron, typically for microscope, it's the best resolution you can get. So if we can think about can construct a nanoscope for optics, that would be very interesting. One of the actually method we pursue is using surface correlations with this surface plasma excitation together. And so we have actually, previously we introduced this flat slab of silver. Now you put actually surface scatters, whether it's one-dimensional or two-dimensional. And you design these surface scatters very carefully. Once actually this far-field optical superlens has two functions. First of all, it will enhance this very large k-vector wave, so-called evanescence wave. Same function we discussed as the superlens before. But however, once the enlarged amplitude of here, you use these surface scatters to forward this or convert this evanescence wave to propagating wave. And that is actually the basic idea. And then everything else can be integrated with a regular optical microscope. But yet you can achieve the imaging at the nanoscale. So these are the simulation result. We show actually 2 nanowires can be separated about 100 nanometers. And you can successfully image them. But without superlens, far-field superlens, you can end up with diffraction limited, like blue line here. So the idea is pretty simple, similar to so this plasmonic system, putting the scatters on the two-dimensional metal film, very similar to electronic system where you have a atom lattice, where you have actually, in this case, this is our dispersion curve, that by introduce this periodic surface structure, you will actually form a plasmonic band gap. At the same time, actually, you can force this band at high K vector into the propagating band. So this is a radiating band, okay? So this actually, for example, simple grating can force this, just like a burning zone, you force this high K into a smaller K in the electronic system. That enables you actually to make this surface-bounded localized mode become propagating. Now, once they are propagating, and they can go to far field to be detected by CCD, for example. But however, we have a problem here. Once we detect that CCD, this is the signal from everything. So you need to know which band it is come from, right? That presents a practical challenge. So the solution we have is, first of all, we design actually a structure or surface scatter such that has a very specific transfer functions, okay? That only forward, in this case, a first band into the propagating band, such that you have a one-to-one relation. So you can unfold it when you do image construction. And second, now, how you're going to do at a higher K. So this gives us about lambda over A resolution. It's not perfectly, going to extremely high, lambda over 20 or something. But as a first step, actually, we are going to try that. Second, actually, we are trying currently now to scanning this band by structural illumination, such that you can scan this band actually at a different band. So that gives you the possibility to access even higher K vector. But keep in mind that the challenge here, actually, the methodic system itself has a loss associated with. So this is the last year experiment we recently published in January, that you have 2 nanowires, actually, spaced about 17 nanometers. This is typo, should be 17 nanometers. 50 nanometer width of the wire. With the best optical or immersion microscope, you cannot resolve them because they are way below diffraction limit. But however, with this far field super lens, you will be able to resolve them successfully. It's interesting because this is plasmonic system. So if you use actually only S polarization, you turn off the surface plasma, essentially, and you're not going to see this enhancement across this slab, such that this actually gives you a blur image. But however, if you actually use the P polarized plus S polarization, that excited surface resonance gives you the very clear image. So this is actually a cross-section of this image. Different approach are taking actually that different from what I just explained for the surface scatter. The other approach is build a so-called hyperlens. Now, this hyper doesn't mean actually it's step beyond super. Hyper because actually we engineer this dispersion inside of this media. It's a hyperbolic. So that's called hyperlens. Essentially, this multi-layer of metal dielectric system, everything is a sub-wavelength, okay? So these are about 30 nanometer each of layers. And what you actually carefully design this such as the dispersion is no longer a circle or elliptical, as we see in regular optics, rather is hyperbolic. What happened is you can engineer, so one actually of the electrical permeability larger than 0, the other is elective along the R direction, or vice versa. And such that the waves actually get into a very large K vector wave, once they get into this media, become propagating. As long as they are in the green curve, they become propagating. And as they propagating out, the tangential photon momentum has to be conserved. So it's like a figure scattering. So when you actually fold your arm in the ice, on the ice scattering, where you spin faster, and when you extend the arm out, you spin slower, right? So when this wave propagating out, that actually tangential component has to be conserved, such that the R goes larger and K theta has to be smaller. So you continually compress this tangential K component until you reach the propagating band at the vacuum. And that is actually essentially is like a photonic compressor. You compress the momentum all the way, actually continuously. So this is the experiment we recently did that essentially we fabricate this structure that with the cylindrical geometry where you have multi-layers of silver and aluminum oxide, each of about 30 nanometers. And indeed, actually, you can make this very high K-vector propagating and eventually become a propagating at the vacuum or a positive medium, in this case, glass or air. And this is the first experiment we demonstrate about 150 nanometers. So it's not a very high resolution yet, but we demonstrate essentially the new principle for hyperlens, where you can image them at the far field CCD about a meter away. This is without this hyperlens, you cannot resolve them. So this actually is coming out this Friday in Science to be published. Now, one actually thing we have to keep in mind for either superlens or hyperlens, there is one thing still, even though we can project a diffraction image below diffraction limit. However, the object still has to be near the lens because actually you want to collect the excited surface plasma before evanescence wave decay too much. So that's still one of the bottleneck. I call it the $1 million question, and we don't have an answer yet. One of the actual solution we are currently developed is to take this plasmonic lens into flying at high speed. So idea is actually build a small flying vehicles that is essentially, it's a small airplane, if you call it, that can fly at the gap of 20 to 30 nanometers. Now, actually, this technology is adapted from magnetic storage writing technology, where in the hard disk, you can have that flying head as well. So we collaborate with my colleague, Professor Buji in mechanical engineering, that he's expert on air-bearing design. So this small airplane design essentially has to be able to fly about 20 nanometer high at the speed of 10 meters per second. So if you scale everything up, and this millimeter size of flying vehicle, it's about airplane flying at the 6-inch high on the back, on the tip of the grass, conformally. Okay. So right now our test shows actually flying at 10 meters per second is about 1 nanometer plus minus actually. So it's a very stable fly and very, of course, the surface has to be relatively flat for lithography. So this actually partially solved the problem that we can keep everything, or either for imaging or lithography, that at the near field, 20 nanometer near field, but yet you can have actually either imaging funnel through this plasmonic structure into for lithography or vice versa to do imaging at the far field. So that enables the possibility to do very high speed imaging and manufacturing. So idea is actually put thousands of these are a few micron size of plasmonic lens into those millimeter structure. And you can do a parallel writing at the same time. And this is the hardware we built it, actually. And this is already, some of you probably can see in my lab tour this afternoon. We recently already demonstrated array writing as well as the, so right now we haven't integrated the high speed modulator, optical modulator yet. So we are writing a lines actually right now in this case about 80 nanometer size. Next, I'm going to talk about different applications or physics where when you actually bring these plasmonic atoms and molecules into an entity. So as we know that in the nature atoms, if you have hydrogen, and if you have bring a hydrogen atom is very reactive. If you bring two hydrogen atoms together, if you form H2, that is very stable, is molecular. When you bring two of them together, you have energy split, very simple. Now, here, if we have a plasmonic atom, namely in this case, it's nanometallic particle, for example, and can be a magnetic particle as well as we design. Depending on how they interact, and different interactions gives you a different energy level, similar to atomic system. So we studied actually about 4 years ago 2 metallic particles, and we tried to write actually these metallic particles use E-beam at a different distance. We spaced them at 100 nanometer all the way to 300 nanometers, and try to see how the total system resonance looks like. And it's pretty simple, actually. You can observe a redshift as you bring the 2 particles getting closer and closer. It's called redshift. Why is that? I use this mechanical spring resonator to show here. It's pretty easy to understand. You have two plasmonic resonators, which essentially is a charge oscillations on the particle. When you have electric field this way, when they are getting fairly close in the near field, where the positive charge and negative charge is going to start to talk to each other. That will retard or reduce the spring constant, essentially. So the resonance of this system can be reduced, omega equal to square root of k over n, right? So if the spring constant k is reduced, the omega is reduced, so that's redshift. So that actually explains simple model. But actually, we also did the FTTT simulation I'm not going to show here. So why this is interesting? The interesting thing is we demonstrate in 203 is actually if you plot the redshift versus particle distance essentially is monotomically dependence. So essentially, by reading the peak shift, you can determine what is the particle space. That gives you the possibility of so-called plasmonic dimer as a long-range molecular ruler. For example, if you have two nanoparticles, if you have DNA in between, you don't know the length of DNA or any organic or biomolecules. By looking at the overall system resonance redshift, you can tell what is the distance between them, and from this a single curve dependence, right? So that actually is interesting because the FRET technology was originally invented actually at Berkeley by Xiang Weiss. That is a very interesting technology today to look at the biomolecular distance between 1 to 10 nanometers. But above 10 actually is very hard to achieve this electronic resonance transfer. So this provides a possibility to extend that all the way to about 200 to 300 nanometer range, which afterwards that optical, regular optical microscope can pick it up. So this actually dependence provides a possibility for long-range imaging of the distance. And about 2 years later, a group in chemistry here successfully using DNA demonstrate it is indeed can be used for biological imaging. Use the DNA, different lengths of DNA. You can actually look at the different colors, essentially peak shift. You can tell what is the distance of this DNA length. However, actually at the time, I also asked my student to look at, can you make a two nanoresonators spacing few nanometers? As you know, the E-beam is very hard to write two dots actually space at 2 or 5 nanometers. So we decided to step two resonators on top of each other using a silicon oxide layer to control the spacing. As you know that silicon oxide today can make 1 nanometer easily as a gate oxide, as a industry to do, even at our microlab, you can do that, few nanometers. So in this case, actually now we are coupling the two resonators vertically. We call it a nano burger. So basically, it's a metal dielectric metal. This is an experimental result. We spaced at 5, 15, 25 nanometers, and we observe a clearly blue shift instead of a red shift. Why? Actually, this is again a mechanical sort of model to show that now they are rejecting to each other in terms of charge, making the spring constant more stiff. That gives you the frequency goes up and blue shift. And so why we want to do this? Because actually we want to use this silicon oxide, essentially the thickness of the silicon oxide. It is the attunable spring, essentially, between the two resonators. And by using a different this thickness, you essentially achieve resonance at a different frequency. This is especially useful for the surface enhanced Raman sensing. So as one application, we collaborate with Frank Chen at LBL and UCSF. We use that for early diagnostic for prostate cancers. UCSF, many of you know that is a medical school across the bay from here. So essentially, this is the nano resonator, a couple of nano resonator. We have a peptide linked with Raman reporter, where we design actually this peptide, which can be cleaved specifically by a group of PSA enzyme. So if a patient has this biomarker, which means actually he has a cancer, that actually essentially that will cleave this bond here, that Raman reporter can be drifted away. Now what, actually I didn't show the simulation result. what the field actually around this resonator is extremely strong, about 10 nanometer around this nanoresonator. After that, it decays dramatically. So if this actually drifts 10 nanometer away, you don't see it. So once we see actually signal drift drops down, we know actually there is an enzyme comes in specifically react with this bond and actually remove the reporter. Next, actually, I'm going to show probably quickly about the two-dimensional optics we are currently doing with the plasmonic lens and tunable. So we actually, we show here a simple plasmonic lens. It's a metallic slab, actually, made by silver or aluminum. You cut it with FIB or E-beam. Essentially, it's a slit on the metal film. The slit works in, I use this as an example, actually. Well, this round or elliptical, you can actually launch the surface plasma from the edge of the slit. And they are travel towards the center. Essentially have a constructive or deconstructive interference. And as we see here, you can focus that at a focal point with this elliptical structure. This actually slit works as two functions. One is a coupler to the far field, because slit provide all kinds of k-vectors. If the k-vector matches with the surface plasma resonance, that launches the surface plasma wave, two-dimensional surface wave, essentially. And you see actually the interference here. And this is the photoresist imaging, basically show you the focus. Now, next question is how you tune them. So if you can focus them to the scale, actually, which is below diffraction limit, let's say 50 or 100 nanometers, how you're going to tune them 10 nanometer or 15 nanometers. So we developed actually a very simple method. You tune the angle of the incident. Essentially, you give an extra photon momentum to these surface waves. However, the magnitude doesn't change because that's dictated by the dispersion curve. But however, it's just like riding a bicycle. There is a basketball hitting on the rider on the side that you make a turn. So essentially, this making a turn originally focused to the center, that can move that off the center. Basically, this little bit of extra photon plasma momentum you provided from this angular incident. And we developed actually a simple analytical theory describe it. And this shows you the experiment show that essentially with a normal incident, everything focused at the center. And with a 7 degree, you can tune it upward a little bit. With 26 degree, it's tuned even more. Now you see actually a strong aberrations because this is the more like a ball lens. This is a two-dimensional circle lens, essentially. But in the ball lens, you have a very large geometric aberration. So if you do an elliptical, thin elliptical, that aberration can be countered significantly. Finally, I'd like to conclude my talk with some of our kind of past work, not related with optics, but it's similar in acoustics. So when you write acoustic equation with the Maxwell equation, they are very similar. Okay. And last year when I visited Madrid, Mayor Plaza, and there was a gentleman actually playing music with all these wine sort of cups here, and each of them filled with different level of the water. Essentially gives you acoustic resonators. And they are coupled, they are touch each other. And he used his fingers essentially play a music very nicely. And at the same time, actually, about 2 days later, I gave a talk at University of Madrid. And about the other type of work in so-called acoustic metamaterials, where we built actually acoustic inductance capacitance with these Helmholtz resonators, essentially. That you build an array of them, essentially that can exhibit very intriguing acoustic property or phononic property that gives you elective stiffness. As we know that most of later materials, the stiffness are positive because when you K equal to Hooke's law gives F equal to K times delta X, right? K always positive. But if K elective means that if you press something actually, instead of going, that goes out. So that actually was some recent work. Now we are looking at how we manipulate phonons and towards the high frequency. And we have a small project funded by DARPA looking at the possibility, well, very futuristic, looking at the mechanical computers beyond the CMOS. So finally, I'd like to acknowledge people fcontribute to the work, and they actually, some of them are former students. David Yan, now he's an assistant professor at the Tsinghua University in Taiwan. Nick Fang, he's also on faculty at the University of Illinois at Urbana-Champaign. Chen Zhang, he's our senior scientist in the center right now. Actually, today he's interviewed at the Northwestern for a faculty position. And we have actually, Zhang is actually currently in postdoc in my group, and various of other student postdoc contribute to work. My collaborators, Basov, Smith at UCSD, now Smith at Duke, John Pendry at the Imperial College, and also my colleague here at Dave Bougie at the engineering department here. And this is funded by a few grants over the last 6 years. ONR Muri on metamaterials, this is probably the first metamaterial program in the US. Now it's coming to the end. We are continuing this effort with Air Force Muri on Plasmonics, starting last year. And also starting last year, we have Army Muri on molecular index at optical frequency. And also overall, there is funded by NSF Nano-scale Center. Recently, we obtained a new center for nanomedicine, combine Berkeley and UCLA for medical school, actually, for developed various of interesting applications for Plasmonic in optical diagnostics. Thank you.
So we're running a little bit late, but we have time for a few quick questions. Is there any questions? Actually, I have one.
Sure.
How small can you make these things? I mean, the wavelength of light is 400 or 500 nanometers, and these structures you're making are, how big do they have to be? 30 nanometers? Like, is it a tenth of wavelength you're looking at? Or?
Yes. So got to be sub-wavelengths so that you can apply the effective medium theory.
Well, I mean, how sub? Like, is it?
Well, typically a lambda over 3 or 4 at least. So 3 or 4, factor of 3 or 4. But preferably as small as possible. That's why actually, as many of you are prospective students, we have a terrific facility here at the LBL, and also on-campus microfabrication facility. That actually is a $40 million facility that gives you probably the best fabrication possibilities in the country to fabricate things that it's impossible at other universities.
Any other questions?
For the 2D plasmonic lens work, where do you see the maximum constructive interference buildup to be? Is that anything approaching the near field strength for, say, spatially resolved SARS?
Yes. So eventually, if you can focus the light, so these two-dimensional waves are way below diffraction limit. So if you say, well, wavelengths of these waves are about 50 nanometer, you will be able to focus the wave to 50 nanometer, so below free space diffraction. But however, it is still diffraction limited by the surface wavelengths. So if you generate 10 wavelengths, so for example, we are now also looking at the other topic, matter wave, atom optics, where the wavelengths can be very small. Of course, the experiment can be very challenging as well. So if the wavelengths matter wave can be 1 nanometer, and you may be able to achieve the 1 nanometer focus. But right now, we are comfortably about 50 to 100 nanometer focus. So that gives you the spatially resolved if you want to do some service and so on.
Any more questions? Then let's thank the speaker again, Professor Zhang.
Thank you.